All right. So we are going to look at this graph of Alice going for a walk. All right. So we're looking for a time, is Alice's distance from home 0 miles? Hint, there's actually 2 answers to this question. At time 0 hours and 7 hours. She went for a long walk. So 0 hours and 7 hours. It was a hike. I guess I should call it a walk. She went on a hike here. All right. What is her maximum distance from home, and when did that happen? So how far away from home did she get, and when did she turn around? All right, 8 miles was the furthest that she got at time 5 hours. That's why we say our maximums and minimums like that. It's like this maximum at this time is when that happened. So what was the total distance that she traveled? Good, because she went 8 miles away. That was the furthest, and then she came 8 miles back, so 16 miles. We're assuming that it's along a straight path. Like she went away and she came back, because I get that there could be the argument, well, what if she went this way and came back a different route? You know, like we're assuming it was a straight path that she went and she came back. Okay. During what interval? Okay, so an interval involves 2 numbers from this time to this, because it's funny, I'll be like, on what interval? And people are like 3. I'm like, so it's from when to when did she walk fastest? It's 6 to 7 hours. And how do we know? Like, why 6 to 7? Because you can kind of just look at the graph and say, slope is greatest, steepest there. I understand it's negative, but that's because she's walking back towards home. What was the speed in miles per hour? This is a rate of change, something per something else. She went down 5 over 1, 5 miles per hour. Nice job, Vince. You don't believe how much calculus there is just in that one little statement. Like calculus is rates of change, and that's just huge for the fundamentals of the subject, right? During what interval, so from when to when did she walk slowest? Yeah, she got lazy. Like what happened there to Alice, right? 3 to 4 hours, and she went, what do you want to call that, like half a mile per hour? Yeah, you almost can't walk half a mile per hour if you try to, like it. Yeah. That's how we feel. That's the speed that the person in front of you down the hallway is walking most of the time. All right. Well, that would be related rates, and we'll get to that later this year, how your rate relates to someone else's rate. Okay, so we're going to talk about that too. What was her average rate of change between 0 and 2 hours? We're going to draw a line connecting them and find that slope. All right. So between 0 and 2, if you want to connect those. And because it's from 0, like starting at 0 to 2, you can probably just count the little boxes, how much up and how much over it went. But I know where I'm taking you on this journey. So I want us to write out the points. So 0, 0, and 2, 5. You're going to have to look at your own grid on this, because otherwise I'm going to have to keep sliding this paper up and down, and I don't want to make you seasick. So you do have it in front of you. Okay. So the slope, you would do 5 minus 0 over 2 minus 0. So it would be 5 halves, or 2.5 miles per hour. So we drew a line on the graph connecting this. What we're going to do is bring that in. We looked from 0 to 2. Now I'm bringing it in a little bit. What did I make the interval in this one? A half an hour to an hour and a half. So it was 0 to 2, and I'm like zooming in a little bit. So let's find points for 0.5 and then 1.5. And we're gonna have to kind of like estimate, and I'd like to keep everything at like a quarter, a half, or 3/4, just like the ease of doing this. So if we look at a half, where we find where that hits the graph, can we call that 2.5? Like this point right here? Like, can we all agree on that? Like that's 2.5. And then if we look at where 1.5 is, that's almost 5. Can we call that 4.75? Just to agree on it. Okay. And I'm gonna connect this. Now my art skills are not perfect, but do you see how the slopes of the two lines I drew in are not exactly parallel. Like it is a little bit different as we brought it in. All right. Let's do the slope between those. We have 0.5 comma 2.5 and then 1.5 comma 4.75. Again, I'm trying to keep them all to quarters, halves, or 3/4, just to keep things, you know, as simple as possible here. So subtracting, we'll have 4.75 minus 2.5 over 1.5 minus 0.5. So think of like dollars and quarters. Like if you think of money, sometimes that helps. So what's that going to be in the numerator? 2.25 over 1, which is nice because that's just 2.25 miles per hour. All right, and then I'm going to bring it in again. So we had from 0 to 2, and then I brought it in 0.5 to 1.5. Now I'm bringing it in even further. We've got 0.75, so 3/4 of an hour, and 1.25. So looking at the graph here, I ended up sliding this down anyway. At 3/4 of an hour, can we agree that that's like right here? We'll say that's 3.5. And then 1 1/4, let's say that that's 4.5. I'm going to connect those. It's kind of hard to see because I'm getting so close to 1 there, which I hope that you understand that's where I'm leading you on this. All right. So if we connect those, again, do you see how that slope is slightly different than the other two? Again, I know my art skills aren't great, but it's like we're zooming in on that point. So we said this was 3.5 and this one was 4.5. Close enough, like good enough. And so if you do that slope, 4.5 minus 3.5 over 1.25 minus 0.75. So the numerator is going to be 1. What's the denominator? Yeah, 0.5. Okay, that's 1 over 1/2. When you divide by 1/2, it's the same as multiplying by 2. You're reciprocating. So this is going to come out to 2 miles per hour. So question 6, 7, and 8, where I'm leading you here, it says use the answers to the previous 3 questions to estimate her instantaneous, that's at one particular moment, instantaneous rate of change at 1 hour. So it was between these two, and then it was between these two. You know, can we say it's 2? Like as we were kind of zooming in on this, we had what, 2.5, and then 2.25, and then it came to 2. Let's just say it's approximately 2 miles per hour. I usually get somebody that's like, well, maybe let's say 1.9. Close enough, like 1.8, 1.92, 2 miles per hour, you know, close enough. Did that feel like a limit? Because that's what I was trying to get across. That's the whole point of that. Like, that's why I do that. I'm not trying to bore you or waste your time at that. I want to get across that what we did there is a limit. You're zooming in on that point. Because we do so much with derivatives, and then at the end of the year, people forget that a derivative actually is a limit. So I just want to like extra stress that, okay? Explain in your own words. We'll just have a brief conversation and then jot something down. The difference between an average rate of change and an instantaneous rate of change. So before we write anything, what's an average rate of change? Change over an interval. That's regular old algebra 1 slope. Okay. What is instantaneous rate of change? At one particular moment. Okay, and I abbreviate these average rate of change, and like my students end up calling them AROC and IROC, which I'm fine with you doing as long as you know what it actually means. So average rate of change is over an interval. So what you can't forget there is that an interval involves a starting point and an ending point. So you would need 2 points, all right? That's over an interval. Instantaneous rate of change is at 1 point. Let me darken that up. This is algebra. This is calculus. See the difference? Okay, but they are both slope. And that is essentially what calculus boils down to. About half of calculus is slope. If you are ever stuck on a question, you don't know what to do a slope, because generally you'd be headed in the right direction. All right, so I'm going to draw you a nice picture here. I think a picture is worth an infinite number of words, so I use that to explain our difference between our average rate of change and our instantaneous rate of change. Just draw yourself, I usually do like an exponential graph, to draw yourself a swoop, something continuous that just goes like that. So here's X. And so that point on the graph, the Y value would be f of X. You input X, you get back f of X. And then what we're going to do is we're going to travel down the x-axis a distance of h. Don't get hung up on that. It's just a letter of the alphabet that we picked to represent that distance. So what would this point right here be? If we start at x and we go a distance of h, this would be what? Yeah, x plus h. And so that point on the graph, that output value would be f of x plus h. I realize that ends up feeling like we're trying to jam every letter of the alphabet into this, but did you all follow me? X plus h, then f of x plus h, just the inputs and the outputs. Okay, I realize it's a lot of letters, but it's just your functional values, input and output. All right, so your average rate of change is your slope of what's called a secant line. And a secant line hits the graph at 2 points. The other place you see this in So if I connect these 2 points, like we did with Alice and her 7-hour hike over there, we're going to do the slope between those 2 points. So we're going to subtract the y values, subtract the x values. So it would be f of x plus h minus f of x. That's, subtracting the y values. And then if you subtract these x values, it would be x plus h minus x. So that's just going to be, just h. The x's are going to cancel out. All right, and that is what's called a difference quotient. Have you heard those words before, difference quotient? No, okay. No, or like it's just been too long. Well, and if you took this course in one semester last year, it happened so fast that difference means subtraction, quotient means fraction. So it's a fraction that has subtraction in it. That's what that is. So that's your difference quotient. Again, this is regular old algebra 1 style slope. It's, if you just want to put rise over run, like, whatever you learned in algebra 1, that's regular old algebra 1 slope, right? That's algebra. All right. Instantaneous rate of change is slope of a tangent line. And again, to relate that back to something you have seen before, whether you remember it or not, when we did this circle unit, remember when we did the line that came by and the circle of that line? You're not pretty well.
Oh, that line.
Never going to turn up. It just comes down, it's like, that's a tangent line. Right? And that's why it's instantaneous, because it's at one particular moment. All right, so here's what we want to do. And don't draw this on your paper because I don't want you to mess up your paper. But what I'm going to do is slide this point this way. And it's what we did with Alice on her walk, okay? So if I slide this point down here and then connect them, and then I slide it down here and I connect them again, and I slide it down here and connect them again and again, it's eventually going to land right here and I'll have a tangent line. So what did I do to that distance h? I want that distance h to be what? 0. So it is limit as h goes to 0 of this difference quotient. And that is the thing that you want to like put a box around with stars, or if you have another color or a highlighter or something. That is the big thing that we were headed towards here. That is your derivative. All right, that is your definition of a derivative. So here's some notation that you'll see for a derivative. You'll see f prime of x. It's not an apostrophe. It's like a it's called a prime mark. F prime of x, or you'll see y prime, or you'll see dy dx. All of those things mean derivative. Okay. Now that will give you a general formula for a derivative. So you'll get, something that has a variable in it and you can plug in. Okay. If you want the derivative at a specific point, the formula changes a little bit. So like this would just be the general formula for a derivative. But if you want the derivative at 7, do you get what I'm saying? Like at a particular value, it'll be limit as x goes to c, c being that number. It'd be like limit as x goes to 7 or something like that. And again, it's just a difference quotient. Let me write it out and then you can look at it. It looks like a slope. It's subtracting the y values, subtracting the x values. It's another way of saying the same thing. F of x minus f of c over x minus c. Bless you. So again, this gives you a derivative, just a general formula. You can plug whatever number you want in. This kind of bypasses that, and it'll only give you the derivative at a specific point. I know a lot of this seems really abstract because we didn't do an actual problem yet. Let's do a 2-minute brain break, and then we'll put some actual numbers to the thing, and then it kind of will make sense. All right, so before we do this problem here, and I just put a whole bunch of parts to it so that we can use the same equation for all this, I am actually going to highlight some of this stuff. So again, this is your definition of a derivative. Once we start finding a derivative, find a derivative, find a derivative, people forget what a derivative actually is. So I just want you to remember, it is slope of a tangent line or an instantaneous rate of change. And then these are the two formulas for it. This is at a specific point. But if I ask you what's a derivative, you should be able to say it's an instantaneous rate of change or a slope of a tangent line. Okay. It's like so important. I know you're like, why is she nagging us? Because it's really important. A car is traveling according to that function that's given right there for 2 hours. X is in hours, d of x is distance, that's in miles. Speed limit is 55 miles per hour. So we have miles, we have hours, we have miles per hour. Are we all together? What's going on? Okay. It's like Alice going for the walk, except it's a car. Find the average rate of change on 0 to 2. What's that asking us for? Slope, yeah, just between those 2 points, a slope. All right, so we need a point for 0 and we need a point for 2, and then we're going to slope them. Yeah, I use slope as a verb for that. All right, so we're going to plug 0 into the function for x. If we do that, what do we get? 0, which makes life easy when you have 0, 0. All right, plugging in 2. 2 squared is 4 times negative 25. That'd be negative 100. Plus 200, so 100. Yeah, they are really nice numbers. If it's non-calculator, you have to have nice numbers, which then once people realize that, they're like, oh, I really like non-calculator. We don't want to do, the calculator problems are like a disaster. They're so messy, the numbers are awful. So non-calculator is much better. All right, so 100 minus 0 over 2 minus 0. It'll just be 100 over 2, so 50 miles per hour. That is the average rate of change of the car over that interval. Does that mean that the car was going 50 miles an hour the entire time? No, it just means that the car averaged that. So the instantaneous rate of change at a particular moment is a lot more valuable to us. So let's find the derivative. Don't hate me, it's just the formula, okay? Foreshadowing, this is going to get about this long. It's going to be a little bit of writing, but then a bunch of stuff's going to cancel. It's going to be all right. Limit as h goes to 0. Here's the formula. Oh, this thing is just always in the way. Move that over there. All right. Limit as h goes to 0. F of x plus h. That means you need to plug x plus h into this function. So it's going to be negative 25 times x plus h squared plus 100 x plus h. So we plugged x plus h into the function. Are we all still on board? Okay, then it's minus f of x. So it's minus the function. Just make sure that you give it a hug, which by that I mean put parentheses around it. Do you guys remember me saying that? Give it a hug? Okay. I say that just to be silly and get everyone to remember stuff. So minus the function, and then this is the annoying part. The whole thing is over. Okay, this is going to be a whole big lot of algebra. All right, now I won't take off, but my suggestion is continue writing limit as h goes to 0. Technically, it should be there. Also, you have to plug in 0 at the end for h, and if you don't write it, you might forget. All right, so this is going to be negative 25 times x plus h squared. I'm going to write this off. When you do x squared, that means this, and that's if you want to write it in margin, that's fine. I just think 0 towards eventually doing this kind of thing, right? X times x squared. This, oh, you guys are cool. Okay, so the outside of x h, 2x and then plus h squared. We want to distribute, what was it, a negative 25 through that. All right, so it's going to be negative 25 x squared minus 50 xh minus 25 h squared. That's actually the hardest part. So we just did the hardest part though. All right, now you're going to distribute a 100. And I love this. You guys aren't even looking at me. You're just all looking at your paper and do, that's good. Do that. All right, and then you're going to distribute this negative. So that'll be plus 25x squared minus 100x all over h. If you have done everything correctly, most of this should cancel out. And if it doesn't, that means you lost a negative sign, is what happened. All right, so call them as you see them. What goes away? All right, negative 100, positive 100x. Those are gone. 25x squared, negative 25x squared are gone. That might be it, but that's pretty good. All the terms that are left should have an h, and that means that you can factor an h out. So if you factor out an h, you will be left with negative 50x minus 25h plus 100. And the whole point of that is h's cancel out. So here's your derivative. You want to write f prime of x equals, that's your derivative. Or I guess you could write d prime since it was d for distance, whatever, doesn't matter. The reason I always say write the limit is at the end, you have to plug 0 in for h. The h should be gone. Your derivative should not have an h in it. You have to plug in 0 for h. So this minus 25h, that's going to go away because that'll be 0. And so your derivative is negative 50x plus 100. That is a general formula for the instantaneous rate of change. If you want the instantaneous rate of change at a particular value, you have to plug in that value. All right. So C says find the instantaneous rate of change at 1 hour. You have to find f prime of 1. You have to plug 1 into that derivative. So if you plug in 1, that'll be negative 50 plus 100. So 50 miles per hour. That still does not mean that the car was always going 50 miles an hour. It only means that the car was going 50 miles an hour at time 1 hour. So we still don't know what it was doing the rest of the time. So D says find the instantaneous rate of change at time 1 hour using the other formula. I threw this on here so that we could practice using this formula as well. And I want to show you that it comes out to the same thing. So if you're like, Ms. Cole, this is a little redundant. Well, I wanted to do an example using this one too. You know, I wanted to show you how to use it. So if you want to bypass all of this, you would do limit as x goes to 1. This one doesn't have h in it. We're just going to go straight. It's like you're getting straight to the value that you want. Limit as x goes to 1. And then it is the function. So negative 25x squared plus 100x. Move this thing again. So it's the function minus f of c. In this case, c is 1. And I think we already plugged 1 in. No, we didn't do that yet. If we plug 1 into this function, that's going to be negative 25 plus 100. So that will be 75. So minus 75. Because the problem said so. It said find it at 1. That'll be given to you. Yeah, like that part has to be provided. It'll say find the instantaneous rate of change at time whatever. So yeah, that'll be provided. All right, so now we need to factor this. Spoiler alert, if you plug in 1, you're going to get 0 over 0. You can test it if you want, but I'm not lying to you. It'll be indeterminate. You've got to get something to keep from. All right, so what can we factor out of the numerator? Yeah, and good. I would take out a negative 25 just to clear, to clear the negative sign. So that'll leave you with x squared. What is that? Minus 4x. Bless you. Plus 3. That looks a ton better, like just already, right? All right, so this will be limit as x goes to 1. You got negative 25. You know what? That was silly. I knew that wasn't going to fit. I'm going to come down to the next line. I tried, but it didn't work. All right, so that is going to split x minus 1, x minus 3. Please stop that. And then those cancel, and it's like, woohoo! Once you get that to cancel, then you can plug in the value that you're approaching, which in this case is 1. So 1 minus 3 would be negative 2 times negative 25 is 50 miles per hour. Like, no kidding, Miss Cole, it came out to 50. I'm trying to illustrate for you that it'll come out the same both ways. You can either find a derivative and then plug in 1, or this will take you directly to the answer. And usually what I get asked is, why would you ever do this anyway? Well, what if you get asked for the derivative at 1 and the derivative at 2 and the derivative at 3 and the derivative at 4? You're not going to want to do this for all of them. You would want to do this once, get the formula, and then you can plug in 1, 2, 3, and 4. So it depends on what you're being asked. Thank you for heads nodding. That makes sense, right? But if you're only asked for one value, this is definitely shorter. Okay. So did the car ever speed? Well, what did we say the speed limit was? 55. So we're going to take the instantaneous rate of change, that's this right here, negative 50x plus 100, that's our derivative, and set it greater than 55, and see if that instantaneous rate of change, like the speed that it was going, was ever above 55. So we're going to subtract 100. That'll be negative 45. Now, when you divide by negative 50, what do you have to do to the symbol here? Switch the symbol. That'll be 45 out of 50. 45, 50 is, what is that? 9/10. I'm going to write it as a decimal, 0.9, 9/10. So did the car speed? Yes. For times less than 0.9. Now, you can't have negative times, so starting at 0. So I would say the car sped from 0 hours to 0.9 hours. It's just after that, it slowed down enough that it averaged below the speed limit. Okay, and I'm sorry, I was going to give you another break, but we have to keep going because I have 10 minutes and we need to talk about tangent lines. This class is going to be like that. We have to like cover this much material, right? So a tangent line is used to approximate function values close to the point of tangency. And if you do get tired, because I get that you've been taking notes in all your classes and you want to just watch, you do know I am recording this and I will post this filled in. So if you feel like you'll absorb it better to watch and then watch the video later and write it down, you can do that. I'm not offended by that at all, okay? But you do need to learn one way or the other, you have to learn it. So you're gonna have a point of tangency. So what's gonna happen is you're gonna have a graph. You're gonna have this point of tangency and then this line that comes through and just like kisses the graph at that one point. As long as you pick a point that's really, really close to the point of tangency, you can use the line to approximate the actual value. Does that make sense? But like the further away you get, the less good of an estimation you get. So it has to be like really close. All right, close to the point of tangency. You can use this because of what's called local linearity. Local means close to, and it means if you get really, really close to that point, the graph will look linear. Like if you zoom in far enough on a point, it will look linear and it's close enough. You just can't get really far away from the point of tangency. All right, and we're going to use point slope form, which is y minus your y value equals your slope, x minus your x value. So this next one says, write the equation of the tangent line to the, I'm still using the car problem, to the point, or at the point x equals 1, I'm sorry. So to write an equation, you need a point and you need a slope. So what I usually do is set it up blank, like here's my point, here's my slope. And our point of tangency is x equals 1. That has to be provided, like they have to give you that, or you have nothing to go on. Now, the way you get the y value is you plug in 1. I think we did that. It came out to 75, right? When we plugged 1 into the function, it was 75. Yeah, that would be negative 25 plus 100. So it would be 75. I just want to wait for you to find it. Are you good? Okay, so you're going to plug it into the original function. Slope comes from the derivative, and you're going to hear me say that a gazillion times. Slope comes from the derivative. Slope of a tangent line. Slope comes from the derivative. So here's our derivative. If you plug 1 into there, you get 50. So our slope is 50. So you need a point, you need a slope. The point comes from the original equation. Slope comes from the derivative. And once you have that, you just assemble the equation. It'll be y minus 75 I think it has to be positive because it was a car going 50 miles an hour, right? If we plug 1 in here, it would be negative 50 plus 100. Okay. Because we are going to talk about velocity later, which can be negative, like if you're going backwards. Oh yeah, you did that in physics too? Yeah. All right, now this says approximate the distance of the car at 1.2 hours. The reason we can approximate 1.2 using this equation is because the point of tangency is 1. So 1.2 is really, really close. If you get further away from 1, it's not going to work. All you have to do is get y by itself and plug in the 1.2 for x. You don't need to simplify this down. All right, so it'll be 50 times 1.2 minus 1. And then just to get the y by itself, you have to add the 75 over. And that would be in miles, because it's the distance of the car, whatever that is. I think you guys got used to this last year. You don't have to simplify anything as long as it's free response. You can leave your answer 50 times 1.2 minus 1 plus 75 miles. You do not need to simplify that down. And you're better off not, for 2 reasons. One, the exam is what? Timed. And the other reason is if you mess it up in your head and it's wrong, then it's wrong. Okay. Now, question 2, I'm going to post the answer. It is another question that goes through step by step the process we just did. Just does it all over again. These ones, I want to do real quick. I love the table problems. These are my favorite. I save these for last. Table, we have 5 minutes. I can do it. The table, some of you are shaking your head. The table problems are great because you don't have to do any math. Like the answers are literally right. These are great, right? Find the average rate of change of, now you have to read the table correct. Of G on 1 to 3. Average rate of change just means slope. You need a point for 1 and a point for 3. Again, you do need to read the table correctly. So look at column G. 1 gives us what? Yep, right there, -1. And 3 gives us 5. Regular old algebra 1 slope. It'll be 5 plus 1 over 3 minus 1. And if you don't feel like simplifying that, don't. Find the average rate of change of F on 2 to 3. Again, average rate of change means slope. So you're going to need 2 points and then slope them. Now make sure you read the table correctly. Now you're looking at the F column. 2 gives you 7. 3 gives you -2. So it'll be -2 minus 7 over 3 minus 2. I know some of you are like itching to simplify that. Just try not to, because if you mess it up, it's going to be wrong. And it's timed, so just don't. All right, 5. Approximate f of 0.8. 0.8 is really, really close to what? 1. You want your point of tangency to be 1. So when you get your point and your slope, you want your point of tangency to be at 1. So find that point on F. Look at the F column. It would be 142. Slope comes from the derivative. Slope comes from the derivative. So now you want to look at the F prime column for 1, which is 2. And so your equation is y minus 42 equals 2 x minus 1. And to do the approximation, all you have to do is plug in, what was it, 0.8 and get the y by itself. So it'll be 2 times 0.8 minus 1 and then add over the 42. And I will finish this last one. It'll literally take 1 minute. What is 3.1 really, really close to? 3. So your point of tangency is going to be 3. Again, if you get further away from the point of tangency, your estimation isn't accurate anymore. So look at the G column now. It's going to be 3, 5. Slope comes from the derivative. Slope comes from the derivative. So G prime of 3, 6. Gosh, I love the table problem. No math, right? Y minus 5, I love those, equals 6, x minus 3. All you have to do is plug in 3.1 and then get y by itself. So add over the 5. Now, if it's a multiple choice question, you do have to simplify those down until you can get one of the answer choices. So like math skills are still important, but for the sake of time today, I left them alone. And if it's free response, I definitely want you to leave them alone.